The next topic is the application layer. The application layer is a topic of its own. I mean, every app doing Facebook, then we should do a course on how to do a social network. So the goal here is not to discuss all the possible application layers, but more what are the principles seen from below, primarily, that impact the application layer, in particular if you want to do one. And we will talk things like interworking and IPv4 versus IPv6, which are the important things. Here is, of course, the simplest application layer, the one that made the internet popular. And you see that one of the principles is visible here, is that when I access the web from one machine here, I go directly to the server. And if the server sends me a page, and in this page there is a link to another server, I go directly to the other server. Of course, the thing that's in between is the internet with all the routers, switches, TCP, congestion control, all the stuff that we have seen here. One of the principles that we will rediscuss in a second is the end-to-end principle that made this thing possible. As opposed to other networking technologies, for example, in France there was a Minitel and Teletext in other countries, where you go to the server and the server has control of you. When you have doing some interaction, you are slave of the server. Here it's not at all the case here, at least in theory. Let me skip a number of those things that are obvious to you. A bit of terminology. Here is an old application that's called FTP. It's unsecure, so today we use SFTP or SSH or the web, HTTP or HTTPS, to do the same job as was done by FTP. FTP was, when I was a student, we did things like this. If you submitted a paper, you had to submit by FTP. So FTP does two things. It allows you to transfer a file, like we do with HTTP, with the web protocol, but it also gives you a remote shell into the machine where you are connecting to, which is of course very unsecure. But at that time, we didn't care so much. And this remote shell allows you to do a listing, for example, of the files that are in the remote directory. You can upload a file, you can download one, you can delete a file that you have uploaded, etc. So because of that, there are multiple TCP connections. Typically, when you connect to an FTP server, you first open one TCP connection. That is a TCP connection that is used to send the commands. That's the one that gives you the remote shell into that remote server. And then, if one of the commands that you type is uploads something, you open another TCP connection just for uploading this thing. So this is a good example showing all the flexibility that is provided by the layer architecture of the internet. Doing an FTP server is fairly simple, at least if you don't go into the authentication base part. Is fairly simple because the only thing you do is using TCP connections. And the fact that the file is correctly transferred or not is all taken care of by TCP. Now, small questions. The classical TCP is this way. The so-called passive mode TCP is that way. So there are subtle differences, as you can see. And the question is, on all those port numbers, so the FTP port numbers, the default, the well-known port numbers are 20 and 21. The other port numbers are temporary port numbers allocated by the operating system. Which of those port numbers are TCP server ports? Timeout in 5 seconds. The majority says F. Which is the correct answer. So a server port is one where the end is in doing a listen, is waiting for a connection request to come. So that will be the case of port 21. Here we open the TCP connection, so 21 is a server port. Now if you use the classical FTP, you talk here and you say, now I would like to get or put a file. And then when you say that, in fact, you open a TCP socket in server mode here, and you give, through this interaction, you give what is the port number that has been allocated to your local server here. And it is the so-called FTP server that opens the connection to you. So you are the server here. So this is a server. This is a server. But port 20 is not a server port. So that's just to illustrate the fact that server is usually meant to be well-defined ports. So 20, 21, everybody will talk of them as server ports or FTP server, but if we look in detail what is happening, the server is here. Of course, this is in some sense inverse to what one would expect, and the so-called FTP passive mode is in the correct direction. So when we do passive modes FTP, then the FTP server will give the port number on which to open a new connection to do the transfer here. This poses a lot of problems on some firewalls that typically don't like to have servers on, for example, a TPFL. If you try to have a TCP server on your machine, it won't work unless you do something special. Right? Voila. One of the application layers, which is perhaps not exactly an application layer, but formally is an application layer, is DNS, the domain name system. It's an application layer in the sense that it's an application program that uses TCP and UDP, but it's really part of the infrastructure of the internet. And we've used it throughout the course, of course. It's used intensively to replace IP addresses by names. For IP addresses, also for other things, but essentially for IP addresses. Now, it was invented before Google. So when the internet was invented, there was no search engine. Alta Vista was before Google, and before Alta Vista, in order to go to EPFL, for example, there's a conference at EPFL, you submit a paper, then you need to know the URL of the site to which to submit, or the name that you will use for the FTP server. So you had names like epfl.ch /siccom 96, for example. So you had to know those names, right? If you don't know those names, you're lost, right? So it's the computer before the web. You were lost if you didn't have the documentation. Now, one could argue that we don't need it today. If I go to a server, I mean, whether this server is called ssc.epfl.ch or whether it's called just the IP address, 128.178.151.24, doesn't make a lot of difference because I will probably never remember the name of the server. I will go to Google and search for SSC plan d'études, and it will get me to the correct place. So to a large extent, DNS would not be necessary today, but however, as we will see, it is still very useful in the context of IPv4 versus IPv6. DS names are rich and becoming richer and richer. Originally, DS names were made of those domains that are here, essentially 3-letter or 2-letter. So so it's a hierarchical naming system where you name something by, for example, lrc.epfl.ch. The top of the hierarchy is here. A 2-letter domain means a country code. So CH for Switzerland, CO for Colombia, LY for Libya, etc. Sometimes they are reused because they look nice, but they're all country codes. Then there are 3-letter where the top-level domains, the non-country code top-level domains, the most famous of them is .com, .edu, which is for universities, essentially American universities, and .net and .mil. And .org. Those are the old-day internet prefixes. Then, because contrary to what I said a minute ago, people want a lot to have DNS names, and somebody found that after all we can sell any name, for example Nestle or UBS or whatever, your family name, you can buy it as a top-level domain if you want. It will cost you $500,000 every year to maintain it. So if you're Nestle, perhaps you'll do it. And originally, of course, this is all English, so it uses only the English characters. But you can do other characters. For example, a few years ago, some of your colleagues invented a website called EPFL with O umlaut. And this is also possible. In fact, there is a code that translates any of characters of a large set of alphabets. It's called the puny code. It's a very funny code that you can look up on Wikipedia. For example, this would translate into that, which is now, so this is a double hyphen here. This is a sequence of characters that are valid for DNS names here. And there is also a special part of the tree of naming, which is for reverse mapping. It's called the .arpa, and it's the series of names that in fact are addresses. So in DNS servers, we will have records for all the corresponding to the names and separately to those addresses, as we'll discuss. How does DNS work? Well, the simplest is to illustrate this. So Lisa is browsing the web and goes into a page that has, for example, this URL, right? Lisa's computer is connected to a DNS server, or has as part of the configuration, as we have seen from the beginning of a course. You must have at least one DNS server. Traditionally, it's the DNS server of your provider. More recently, companies like Google, for example, are making their own servers available to everybody. So you can use Google's web servers. So whatever web server is configured, one of the web servers, there may be several, then when your browser sees this, of course, the main thing it wants to do, as we have seen already, is translate this into an IP address. We need to know what is the IP address of that part of the URL, which is recognized as a DNS name. So there is a part in your server called in your computer called a DNS client, a DNS resolver, that has the job of mapping all names to IP addresses. Typically, it has a cache, so chances are if you go there frequently, the answer is local in a cache in your machine. But if it is not, you will go to the DNS server and you will send a DNS message, which is an application layer query, which is essentially holding a question: who has, what is the IP address that corresponds to that? In DNS terminology, this is called an A record. So the DNS, the table that is held in a DNS server, is a sequence of records, like in a database, although it's not a formal database, it's just a big table. And the most useful records are the ones that map a name to an IP address. They are called A records. A for IPv4, quadruple A, as we saw for IPv6 here. So the DNS server will receive this. Now, chances are that the DNS server has that in its cache, in which case it will respond directly. But here we study the most interesting case where the DNS server of EPFL doesn't have this in this cache. It can be because it's not a frequently asked question, or because, as we will see, the values have a time to live. The cached version expired, so we need to refresh it. So the server, the DNS server, will now try to find for you the answer. Now, there are two ways a DNS server can work. It can be iterative or recursive. Recursive means I do the job for you. You ask me a question, I will do the job for you, and I will respond only with the answer. Typically, you don't do that if you're a DNS server, except if you're a good DNS server. For example, if you're the EPFL DNS server and you're talking to somebody inside EPFL. You don't do that because that means this server has a lot of work to do. It has to remember the query that it is serving, keep it somewhere in memory, do all the work until it is solved. And this is here signaled when you typically a client sends to its home DNS server, it will ask for recursivity. RD means recursivity desired. Right. Then the DNS server of EPFL doesn't know, so it has to find what is the IP address of www.zurich.ibm.com. For that, the principle is very simple. You follow the hierarchy. So you're asking for somebody that belongs to IBM.com, so you need to find what is a name server that serves .com. Those are called root name servers. There are 13 of them in the world. So and then you will go there and you ask, if you really know nothing, you will go there and you ask, you.com server, can you help me with this? And you will send a question, which is here, with typically recursivity not desired. Even if you say it's desired, you will not get it recursively, because this server is at the heart of the internet and will not do the job for you. So it will give you one answer that will help you. And this answer, number 3, will be, so you've asked this guy about this address. This one will not give you the answer, but it will give you the IP address of the DNS server of IBM. So we see here the principle of how it's organized. If you are IBM or you're a company and you set up a domain within .com, you have to say to .com what is the IP address of your DNS server, and this is the only thing that, or the main thing, that .com will remember about you. So this root server knows about the IP addresses of one or several DNS servers here. So this is the answer that you will receive. You will receive a number of DNS servers. Of course, you will receive there in the form of names, but of course the names are useless. You also give the IP addresses that correspond to this. So when my EPFL server has received this, it has 3 IP addresses of 3 DNS servers of the IBM domain. Still doesn't know, because I'm not looking for IBM, I'm looking for www.zurich.ibm. But it will pick one of them, for example, Watson, and will send a query, number 4. Number 4 is the same query, this one, which is sent again. So you see that, in fact, the same query is sent to different servers, but as those servers are further down on the tree of the name system, we get closer to an answer. So this one, if we would have a very large company, it could answer by giving you, well, this is the Zurich domain inside IBM, so I could give you the IP address of a DNS server of the Zurich domain, and that could continue. In the specific case of IBM, they don't do that, so they give you directly the IP address of all the domains below. So they give me the IP address in particular of this resource, this machine, which is the web server that corresponds to this address. And this is sent back to the DNS server of EPFL. That will keep it in its cache and then send it to me. And only then Lisa can now have the IP address. You still haven't got the web page that you clicked upon, so then the machine will now go to that IP address and open the web page. So that is the story of DNS. Now, using tools like DNS Lookup or DIG, you can go into your own servers and look at all details of the data that they have, if you want to have a snapshot of their table. For example, here, if I look for lca.epfl.ch and I give an A, so this is like sending manually a DNS query to this server with asking for an A record, which means an IPv4 address. So that's the question that is being sent. And the answer, I will have this. So you see that I have the IP address, but in fact, there is here what is called a canonical name. So there are multiple names that correspond to the same address. And one of them is called the canonical name. So it's typically the name of the machine, because a service, like a web service, can correspond to different machines, and you give machines to names. Now you see there's a lot of redundancy. I mean, if we have different machines, they have different IP address, so why do they need a name? But typically, this is done. If I give the same with quadruple A, that means I will obtain the IPv6 address if it exists. In this case, I will have similar. Here is the IPv6 address, as we have known already in the lab for this one here. I mentioned that an important part of this is the cache. So the domain name system is not a database in the classical database sense. It's a database in the sense it's a huge record of all the information, of all the names and their IP addresses. It's distributed, and we've seen the mechanism for distribution. Every domain holds its local table. For example, EPFL has all the IP addresses and all the corresponding names. And this form of distribution means we keep the information local, close to the place where it's allocated. But it's not a true database in the sense that in a database you have what is called consistency. If I book a ticket for a concert on a distributed database, a very popular concert, or a train ticket, let's say, I go to a database. This database is also distributed, perhaps it's hierarchical, but what I want is if I buy a ticket for a given seat, no one else can buy the same ticket for the same seat. So I have the problem of consistency, which is what makes a database so complicated, so difficult, and a theory of its own. Here in the internet for DNS, we relax consistency. So we distribute the information and we keep it locally. So when you go to the DNS server of Google or of EPFL to ask for what is the IP address of ibm.com at zurich.ibm.com, you will get an answer which is cached. Now, if the true address has changed, the cache may have obsolete addresses. In a true database system, you would have a mechanism such that if you ask the cache, first the cache verifies and the central establishes consensus of some kind to verify that the address it's giving is the same that everyone else would give, with all the problems and the beauty of consensus, as you know, is impossible in real systems, but still we do it. Here, we ignore this, so we don't require that the things are consistent, so that if an IP address has changed, all the caches will be invalid, but they will still return the old address. Of course, we don't want that to happen forever, so there is a time to live. Whenever you cache something, you keep it only for some time. So when this server has received the address from ibm.com, it has received in the message, it has a time to live, which is in seconds here. So this is 2 hours. So that means this will stay here, and you timestamp when it has arrived. If within 2 hours this is valid, so any question you will have will use that one. But if, in particular, if there is a change here just after you ask for it, during 2 hours, you will have the wrong information. It's visible also how old the information here. So assume Bart now, a few seconds later, does, or sometime later, does the same thing. It will get some information here with a time to live, which is now less, because when Lisa got it, it was fresh, it was valid for 2 hours. Now this is valid for 2 hours minus 60 seconds, so 1 minute less. So it means if this guy caches it here, you cannot cache it for as long. So the value that is given here is, of course, decremented by the time it has spent here. In one of the labs, we did what is called a reverse-DNS lookup. That's very useful when you're trying to debug something. For example, when we do traceroute, that was in lab 0. When you traceroute something, traceroute will print the IP addresses if you specify the numerical flag switch in the command. But if you don't, you will get the names here. How do you think that traceroute obtains all those names? For example, I'm going to a given destination. I have names that are names that in principle nobody ever sees because they are the name of routers, for example. How do you think that traceroute gets it? Time out in 5 seconds. Well, let's see how it happens. So certainly that would be very expensive to try all possible DNS names and verify each of them with the DNS server. Because we don't know what are all the possible DNS names here. So now traceroute, how does traceroute work? Traceroute is not talking to the intermediate router, as in fact traceroute is simply sending a packet. So depending on which version you're using, it's ICMP or a UDP packet. Traceroute is a UDP, traceRT in Windows is ICMP, but essentially you're sending a test packet to the destination with increasing TTL. You start TTL1, TTL2, and you analyze the error message. So all those addresses are obtained by the source of the error message that we have received because the TTL was too small. So we don't really talk to those routers, we simply receive an error message from those. So the only possible way, perhaps, is to do that. And this is what is done, but it is not done by doing like we would do in a database, a reverse lookup, although it's called reverse-DNS lookup. In a database, you can ask, give me all the names of the customers with this number. And you search through all the numbers and you find the corresponding names. Again, the DNS is not meant to be a database, it's meant to be lightweight and easy and fast. So there is a second table for the IP address to names. So so they do not do a reverse search. Instead, there is, when you are the responsible for a domain, you need to populate 2 tables in the DNS server. A first table that gives all the IP addresses of all the names, and a second table that gives all the names that correspond to all IP addresses in your domain. And hopefully they are consistent, but you can easily check on the DNS servers that are not secure that sometimes they are not, so you can find sometimes inconsistencies. So those records are called PTR, pointer record. So if I go into my preferred DNS server and I ask what is the IP address, the name that corresponds to this IP address. So you need to map this IP address because you're talking DNS, you need to map that into the syntax of a name. And the way it's done is by taking the IP address in dotted decimal notation in reverse order, and you ask for a pointer record, which is this reverse record here. Sometimes you find things like this. For example, if you do a DNS, if you do a trace route to some special places in the world, you find answers like this. So they have routers that pretend to have a name called Freedom to the Galaxy, etc. And if you effectively find, you look up this IP address, you ask for a pointer record. This is the name you find. But now if you try to do the reverse query or ping this name, of course, it doesn't exist. So that's an example of some funny domain owner that puts inverse records that are not the inverse of the true record, just because they like Star Wars. Like BGP, there is exactly the same issue. The basic DNS is not secure because the internet was not conceived with security in mind. And the story is very similar. But unlike with BGP-SEC, the security is being deployed more actively and more rapidly than for BGP routers, because obviously it's even easier to spoof servers by injecting wrong names. So if you say you are www.tpfl.ch with a different name, then anybody who goes to that DNS name will go to a different IP address. So the problem is the same. We need a way to sign the records. And the format on which to do that is called DNSSEC. So some domains like Sweden implement it systematically. They mandate that all servers have to implement it. Some DNS servers, obviously Google does it. Where is the trust rooted? So one problem with all the certificates is I receive a certificate that allows, I want to verify, for example, I go to a DNS server, I get an answer. And I want to verify this answer. The answer comes with a signature, so in the response there is time to leave, etc., plus an attribute which is a signature. I need to verify the signature. How do I verify the signature? By having a certificate that and public key cryptography mechanisms that will allow me to verify that the signature can have been created only by somebody who has the private key that corresponds to the public key that I have in my certificate. But for that, I need to know, do I have the right certificate? So this certificate is signed, and by whom is it signed? That's by somebody who has the root of trust. So in the routing domain, the root of trust is at IANA. In the DNS domain, the root of trust are the root servers. So the one that have the .com, etc. So they are the critical infrastructure. If you manage to hack them, you have control of the internet. Voilà, that's all for today. We meet again tomorrow for a quiz and the lab. Thank you very much.